All right, so the last stuff that we're going to talk about this semester. Where did it go? Just good grief. The last stuff that we're going to talk about this semester talks about solving systems of equations. So that's what we're going to start today. We'll talk about what systems of equations are today. And we will also talk about a couple of methods for solving systems of equations. When the system is what we refer to as a linear system of equations, and we'll define what that is here in a second. And then later on Friday and next week, we'll talk about another way to solve systems of equations, which is really the same thing as what we'll be doing today. It's just a little bit of a streamlined way of keeping track of things more than really a different method for solving. Pardon me. And then after Thanksgiving break, which, believe it or not, is in a week and a half, right? Things are approaching quickly. After Thanksgiving break, we will talk a little bit about solving systems of equations that are not linear. Your last exam will be that Wednesday of the last week of classes, which I think is the 11th. If I remember the correct day. And then final exam in here is scheduled on the Wednesday of finals week, which is the 18th. And unfortunately, they scheduled this at 8 in the morning. So we'll have 8 a.m. final on that Wednesday. But I'll remind of all of that. I just want to give you a little bit of overview of where we're headed. So we're almost done. We've got, I think, 5 sections to cover in Chapter 9, or 5 sections that we're going to cover in Chapter 9. 4 or 5 sections, I can't remember which off the top of my head. But it'll all be devoted to solving systems of equations. That's what the entire chapter is about. Okay. So again, I apologize for not having a handout today. I literally have no idea where they went. I know I printed them. I know I saw them this morning, and I have no idea where they are now. So I apologize for that. Okay. So today we're going to focus on solving systems of linear equations with just 2 variables in them. Because at least it gives us a way pretty easily, as you can kind of see at the bottom of the page here, for being able to visualize what's going on when we're trying to solve these things. So just by a system of equations, what we mean is a set of equations all involving the same variables. So that's all we mean by a system of equations. Usually, we're used to solving a single equation and trying to figure out, say, what x is. That's usually what we do when we solve an equation. What we're going to be interested for in this section, or in this chapter, I guess I should say, we're going to be interested in looking at several equations at the same time and figuring out what satisfies all of the equations at the same time. That's where we're headed. So, but it just as like I said, as a simple definition of what we mean by a system of equations, we've got several equations, maybe 2, maybe 3, maybe 10, but all of them have the exact same variables in them. We're not going to have, the first one's not going to have like ABC, and the next one will have XYZ or something like that. They'll all have the same variables in them. All right. For linear equations, we just mean a system of equations in which all of the equations are linear. Remember that we talked about this a while ago, earlier this semester. Remember we say that an equation is linear when the variables in the equation when they appear, are just to the first power. Okay? They're not inside other functions. So for example, You're not going to take the log of x. That's not linear. It can't be inside the function of another one. You can't divide by it, so 1 over x is also not linear. You can have any x's in the denominator. And you can't multiply them together. So if you see an x and you see a y, they have to be separated from each other with a plus or a minus sign, or on opposite sides of the equation. They cannot be multiplied together. Okay. So linear equations mean when you see the variable has to be raised to the first power, and they can't be multiplied together. So no square roots of x, no 1 over y's, no logs of z, no x times z, none of that, okay? When you see the variable, it has to be the first power. It can be multiplied by a number, that's okay. If you have 3x, that's fine. But x cubed does not. Does that make sense? All right. So by solution of a system, what we mean is just a set of values for the variables that makes all of the equations in the system true. That's what we mean by a solution. If you have, and like I said, in this section, we're going to be concentrating on systems of equations in 2 variables, and usually those 2 variables will be x and y. What we mean by this is that you pick a value for x and a value for y. When you take that value for x and y and plug it into every single equation of the system, you get a true statement. It has to work in every single set. Okay. All right, so what we're interested in for linear equations, besides being able to solve them, is how many solutions can we have? And I'm not so worried about you putting all these graphs in your notes exactly to scale, but let's just talk about what these different pieces are. So notice that when we draw 2 lines, like I have in that first system of equations there, when I graph 2 lines, if you were to put them in slope-intercept form, you should be able to see that you've got 2 different slopes, right? If you solve for y, you'll get a different slope in the first equation than you will in the second equation. Notice when they have different slopes, they cross each other, and they cross each other in exactly 1 point, right? So that's one possibility, and that's what that first example is giving us, is that this system has one solution. And I know it's hard to see because my picture is really, really, really small here. But if I count over the tick marks here at the bottom, I've got 1, 2, 3, 4, 5 for my x. And it looks like 1, 2 up for my y. So it looks like this point is the point 5, 2. I know it's hard for you to see because those are really, really super tiny numbers. I can barely see them on my screen. Zoom in a little bit. They're really, really tiny, but you can kind of see the ticks, right? So again, by what we said a solution is, if that really is the 0.52, when we take 5 for x and 2 for y, it should work in both equations. That's what it means to be a system. Or a solution to the system. It should work in both equations. So if I check that, if I do 2 times 5 minus 3 times 2, I get 10 minus 6. I really do get 4. That one checks. And if I do 5 plus 2 times 2, I really do get 9, and that one checks. So the solution here would be the ordered pair of 5, 2. X equals 5, y equals 2. Does that make sense? So again, the solution would be, we have these 2 lines crossing each other. Look at this next picture. Notice I said something about the slope of the previous ones We got this one had a negative slope, this one had a positive slope, which is not too hard to check if you move everything over to one side, or move the x's over to the other side. What about these two lines? What can you say about their slopes? They're the same, right? And since the slopes are the same, what can I say about the two lines? What kind of lines have the same slope? Parallel, right? Parallel lines don't intersect. So I don't have a point that's in common on both lines. So this one must have no solution, right? So again, here the lines are parallel, and we get no solution. All right, so far we have an example where the system has one solution. We have a system where an example where the system has no solution. Look at this last one. Now we only see one line. Does not mean making a mistake for graphing it. There really is only one line here. What could you do to both sides of the first equation that's up there and get the second equation? What can you do to both sides of the first equation and get the second one? Multiply it by 3. Yeah, that's okay. Yeah, multiply the first equation on both sides by 3, and I get the second equation. So both of those equations actually represent the same exact line. So really what we've done is we've graphed the same line twice. We just graphed the line on top of each other, right? So any point on this line satisfies both equations at the same time because both equations represent the same line. Yes?
I was just wondering what the rest of the definition was for the solution of system equation. Just the last little bit.
Oh, sure. It's okay. This makes all the variables true, or all the equations true when you plug in the values. So again, going back to this example, any point that I plug in that's on the line satisfies both equations at the same time. Well, how many points are on the line? Infinitely many, right? So in this case, you get infinitely many solutions. Okay. These are the only 3 possibilities when you solve a system of equations. It's not possible for a system of linear equations to have exactly 2 solutions, for example. Because exactly 2 solutions, say think about it with lines. If you had exactly 2 solutions, one of your lines would have to bend. In other words, not a line, right? If you had exactly 2 solutions, it had to cross at 2 spots. Exactly 2 spots. And this works in general, not just for a system of a system with 2 variables in it, but a system with any variable and any number of variables that you have. As long as it's a linear system, we'll write this down at the end here. Any system of linear equations has no solution. Oops. Exactly one solution. Or infinitely many solutions. Those are the only 3 possibilities for number of solutions for a system of linear equations. That's all you get. So to give kind of another physical example, besides just the graphs of the lines, when you have a linear equation in 3 variables, graphically that makes what we refer to as a plane. By a plane, some physical representations of a plane might be the floor, or the ceiling, or the walls. Okay? If you look at, say, a system of 3 equations and 3 unknowns, You might represent no solution by, well, do the floor and the ceiling intersect? No. Right? So we'd have no solution there if I was just looking for the floor and the ceiling, right? I hope the floor and the ceiling will ever meet. That would be bad, right? Okay. But if we had, say, two equations, maybe you do the floor, or excuse me, this wall and the ceiling. They have an intersection, which would be the line there, right? And there would be infinitely many solutions for that 2 equations and 3 unknowns. Or maybe you do the ceiling, this front wall, and the side wall. We get exactly one solution, which would be up there in the corner. You can kind of see it that way. Think about how planes can intersect. But again, if it's a plane, it has to be flat. I can't bend it, so I can't get exactly 7 solutions right here. I have to bend it. In any event, that just tells us how many we're looking for in any given case. So how do we solve these things? I mentioned earlier that we'll have 2 main methods for doing this. The first method that we have is referred to as the substitution method. And it's exactly what it sounds like. We're going to solve for one variable in terms of the other using one equation, and then substitute that expression into the other equation. It's literally what it sounds like. Take an expression and substitute it in. So in this example, we've got the system x plus y equals 2 and x minus 2y equals 0. You'll notice that with the notation, when we want to say that we're solving a set, I didn't mention this earlier. When we say we want to solve a system of equations, usually we put a little brace on the left-hand side to indicate that we're treating all these equations as a system, and we're trying to solve them what's called simultaneously, finding something that satisfies all the equations at the same time. All right, so we look at this equation, and what I just said was we want to use one equation, solve for one of the variables in terms of the other, and then substitute that expression back into the other equation. Of those 2 equations, which one do you think you might want to use first to solve for one variable in terms of the other? Which one's easy to solve for one variable in terms of the other pretty quickly? Well, yeah, they're both pretty easy, but if I look at that bottom equation, how can I solve for x in that bottom equation? Yeah, just move the 2y over, right? I can solve that one pretty fast, right? So if I have that x minus 2y equals 0, we can just add the 2y over and we get x equals 2y. And so here's where the substitution comes in. I used the second equation to solve for x. I'm going to use the first equation and substitute in the 2y for the x. Okay? So here's my first equation, the x plus y equals 2. We'll take out the x and put in the 2y. That's the substitution part. This now is a fairly straightforward equation to solve, right? 2y plus y equals 3y. Divide by 3 and get y as 2/3. That gives us the y value for what we need. How do you think we're going to figure out what the x value is? Yeah, plug it in back into that original thing, right? We have x equals something with y's. Just take the 2/3 and plug it in here, right? So if x is 2/3, then if your y is 2/3, then your x is 2 times 2/3, which gives you 4/3. And then a lot of times we'll write our final answers as ordered pairs. And so the ordered pair xy that we're interested in will be 2/3, 4/3. Okay. How many solutions did this system have then? How many solutions did we find? Well, the ordered pair is actually just one, right? There's one solution to this one, right? It's x equals 2/3 and y equals 4/3. So there's one solution. All right, look at that second example here. I'll blow it up a little bit in case you need to see it. See if you can do that one. Work on that second one, that second example there. Work on that one for a few minutes, and then we'll chat about it. You ready to talk about it? Yes, no, maybe. Yeah. All right, which equation did you use first? Did you use the first equation or the second one first? The second one? Notice that the second one is a little bit easier to solve for x right away. There's a coefficient of 1 on it, right? Now I don't have to introduce any fractions. So I would probably do this. It's not wrong to use the first one. It's just that if you use the first one, you're going to end up with some fractions. Okay? So use that second equation, and hopefully it's fairly easy to solve for x in that equation. You can solve for either x or y, doesn't matter. You just have to solve for one variable in terms of the other. Just make it as easy on yourself as you can, right? If you're able to do this without fractions, then do it without fractions. Well, I picked the second. All right, so what do we do with that expression now? Yeah, plug it into the first one, right? So we have the first equation is 4x minus 6y equals 12. So take your 7y plus 14 and plug that in for x. What do we need to do now? Distribute the 4 through, right? So when you distribute your 4, you get 28y plus 56, then minus 6y equals 12. The 28y minus the 6y gives you 22y. Subtract your 56 over, you should get negative 44. So we get negative 2 for y. And then what do we do with that negative 2? Yeah, plug in. We have this expression that says x equals 7y plus 14. So we'll take our negative 2 and plug it in for the y. And figure out what the x value is then. So your x has to be 7 times negative 2 plus 14, which gives you 0. So then again, if we write our answer as an ordered pair, we get 0, negative 2. That one okay? Any questions on that? We're all very excited about learning about systems of equations today, I can tell. We're just pumped up. You got to keep the noise down. Don't disturb people. Okay, apparently that wasn't as funny as I thought it was. That's fine. All right. Let's look at the next example here and see what happens. Again, we'll do substitution. Let's work on this one together. Do you want to work on the first equation or the second equation? We've got 5x minus 15y equals 10. Negative 2x plus 6y equals negative 4. Which equation do you want to work with? The first one? Sure, might as well we use the first one. We haven't done one yet where we've used the first one, so why not? First thing we want to do is solve for one of the variables. Okay, solve for x. Probably be a little bit nicer to solve for x. So we've got 5x equals 15y plus 10. And then divide both sides by 5. We'll get x equals 3y plus 2. So far, so good? What do we want to do with that now? Good. Yep. Take that. What we just found. That expression we just found for x. Put it into the second equation. So we get negative 2 times 3y plus 2 plus 6y equals negative 4. Distribute. We'll get negative 6y minus 4 plus 6y equals negative 4. What happens now? Yeah, notice that your 6y's definitely cancel, right? On that left-hand side. We get negative 4 equals negative 4. All your variables went away, right? So we look at this and we ask ourselves, is this a true statement or is this a false statement? It was true, right? It was a true statement, right? Negative 4 is definitely equal to negative 4, okay? So what we have here is, since this is true, we must have really had the same line being represented by each equation. Okay? So in this case, this tells us that we have infinitely many solutions. And when we have infinitely many solutions, there's different ways that we can represent what the solutions are. We refer to this as we refer to this as a dependent system. What we mean by dependent is that one or more of the variables depend on another variable. What we mean by dependent. When you find exactly one solution, we refer to that as independent. So you have a value for x and a value for y, and there aren't variables involved. So when we write the solutions for a dependent system, there's a couple of ways that we can write it. Here's how I'm going to write it. I need to look at WebAssign to see how it writes it. I forgot to look before class. So a lot of times we'll write this in what we refer to as set builder notation. We're going to write down what the form of the solution, all the points have to look like, and then give a condition on one of the answers. All right, so notice that we have x up here. We have x equals something with y's, right? So we can pick something for y, but then x is determined, right? So the way I would write that as an ordered pair is 3y plus 2 for the x, and then anything for y. So what this says is that I can pick whatever I want for y. Once I pick the y, I know what the x value has to be. So this is a way to write a dependent system. And then we have to say what kind of a thing y is. So let me tell you what this notation means. It's not that big of a deal. This notation here with this funky looking R, that's just a set of real numbers. Basically, you can read this funky little E symbol as is. It's an element symbol. It says is an element of. This just says that y is any real number, is what this says. So again, it just said it's math symbols for what I just said. This says I can pick whatever I want for y. That's the y coordinate. But once I pick it, this has to be the x coordinate. And that's how we express a dependent system. That okay? All right, so let's do the same thing for the next one. Do this with substitution, and then we'll talk about elimination. Which equation do you want to use first? I'd probably use the second equation, right? Because there's a 0 on the other side. So if I look at the 6x plus 3y equals 0, which variable do you want to solve for in this case, the x or the y? The y. So subtract your 6x over and then divide by your 3. And we get y is equal to negative 2x. Again, you could use the first equation if you wanted to. I just think it's a little bit easier to use the second one. What do I do with this now? Yeah, plug it into the top equation. So we'll replace that y with negative 2x. What does the left-hand side simplify to now? 0. And now is that a true statement or a false statement? False, right? This is false because 0 is not equal to negative 5. At least it isn't today. Ask me on a different day, they may be equal. You never know. So since this is false, there's no solution. And that's the end of it. When you have a system with no solution, we refer to that as an inconsistent system. What an inconsistent system means is that there's no solution. It's just that, right? They don't give me consistent information. The first equation gives me a set of values. The second equation gives me a completely different set of values. There's no overlap. So that's what the inconsistent part means. It's giving me inconsistent information. I can't solve them both at the same time. All right. Any questions on how the substitution method works? This okay? All right. So let's see if we can do elimination. Now, the reason why we do the substitution method is because we're really trying to get everything down into one variable. And we do that through writing one variable in terms of the other. With elimination, we literally try to get rid of one of the variables to start with. Okay? So let's look at the system of equations that we have up here. We've got 5x minus y equals negative 21. and 9x plus 2y equals negative 34. What I want to try to do is make my coefficients on either the x or the y to be the exact opposites of each other so that I can add the two equations together and make the x or the y go away. Do you see something that I can multiply one of the equations by or both of the equations by? A different number, you use a different number for each of the equations. But do you see something I can multiply the first equation by in this case to make the coefficient on one of the variables be the exact opposite of each other? Yeah, do a 2 on that first equation, right? So, but start with this equation, or this system, sorry. And we'll multiply that one by 2. So just multiply by 2. We get 10x minus 2y equals negative 42. We didn't do anything to the second equation. And the reason why we want to make them the exact opposite of each other is because I want to add the two equations together and make the variables go away. Okay? Well, I do the exact opposite signs for those so that I can add and it eliminates them. When I add the left-hand sides together, what do you end up with? 19x, good. Because the y's go away. What do you get when you add the right-hand sides together? 76? Yep. And now we can solve for x, right? Now that we eliminated the y, we can solve for the x pretty quickly and get negative 4. So we found the x value, but we also want to find the y value. How do you think we could do that? Yeah, plug it back into, it doesn't matter which equation. It has to work in both, right? So use either the first equation or the second equation to figure out what the y is. I'll use the first one. So we'll plug in negative 4 for x. Get negative 20 when we multiply. Add over, we'll get negative y equals negative 1. And then finally, multiply both sides by negative 1. And so our solution then will be negative 4 comma negative 1 for the xy. That one okay? So that one, we just had to multiply the first one by a number and we got them to match up exactly. Notice in this one, it's a little bit, I can't just multiply, I could have used a fraction. But it's kind of like finding a common denominator, right? So let's say we got rid of the y in the first one. Let's see if we can get rid of the x in the second one here. What can I multiply the first equation by, and what can I multiply the second equation by, so I can make the coefficients be the exact opposite of each other in this case? Yeah, do a 3 on the first one and a 2 on the second one. So you multiply the first equation by 3, you should get negative 6x minus 6y equals positive 12. If you multiply the second equation by 2, you should get 6x plus 6y equals negative 12. What happens now when you add? What do you get? You get 0 on the left-hand side and A 0 on the right-hand side, right? So notice, just like when we had one of those with the substitutions, all the variables went away, right? Did we end up with a true statement or a false statement? True. So when it's true, how many solutions do we have? Infinitely many. Good. So there's infinitely many solutions. So this is when we write that dependent system idea. If I'm going to do a dependent system, I need to take one of the equations and solve for one variable in terms of the other. Okay? So let's just take the first equation. Let's add the 2x to the other side. And then divide everything by -2. So I solve for the y, just to do it different than what we did for the first one. Okay. This is what you have to do when you have a dependent system, to write down what all the solutions look like. Okay. Solve for one variable in terms of the other. Now I get to pick anything I want for x, but then my y is determined. So when you write the ordered pair in this way, x can be anything. Once I pick my x, my y has to be -x minus 2. And then again, x can be any real number. Again, this notation is just saying I get to pick my x, but once I pick my x, my y is determined. That's what we mean by that dependent system again, right? The y value here depends on the x. Your answer might look a little bit different here if you would have solved for the x instead of the y. And that's okay. This one okay? Okay. So let's do this last one real quick. Again, I want to try to eliminate one of the variables. If I look at the 8 and the 20, let's just see how I try to get rid of the x. You could also get rid of the y. It doesn't really matter. I think I can multiply the first equation by 5 and the second one by 2, and then I'll get a 40 for both of them. It's like finding a common denominator, right? So multiply your first equation by 5 and your second equation by 2. When we multiply the first equation by 5, we should get 40x minus 30y equals 90. When we do the second equation, we get negative 40x plus 30y equals negative 88. What happens now when you add them together? What do you get? Zero on the left-hand side and 2 on the right-hand side, right? Is that true or false? False. So what does that tell us? There is no solution. Good. No solution, or another word for no solution is inconsistent. Yeah. Any questions on those at all? We're going to do more examples of elimination. On Friday, we will have 3 variables in those systems, so that will be a little bit extra work. We're going to do more examples of elimination on Friday. The last page of this particular handout is example of the application problems. I'll get the handout posted on Moodle in case you want it. Okay, and I'll bring one to class too. I'll hand it out on Friday, Wednesday, whatever day, Friday. That's right. I'll hand it out on Friday for you. I apologize for not having it today. I literally do not know where they went. So, all right, we'll see you later. Have a good one.